We want to determine a state variable model for this circuit. The state variables need to describe the energy stored in all the energy storage elements. Their choice isn't unique, but we know that capacitors store energy as voltages and inductors store energy as current. So I can define a state variable as a current through this inductor, x1. I can define a state variable as the voltage across this capacitor, x2. And I can define another state variable as the voltage across the capacitor C2, which will be x3. In order to make things easier later on, I'm going to go ahead and label the voltages across the inductors and the currents through the capacitors. So this voltage is L times the derivative of x1 with respect to time. The current through the capacitor C1 is C1 times the derivative of x2 with respect to time, and the current through the capacitor C2 is its capacitance C2 times the derivative of x3 with respect to time. Now I've got my voltage-current relationships for the energy storage elements taken care of, along with the passive sign convention. I don't have to remember that anymore. Now I just need to do KVL, KCL, and Ohm's law to write three differential equations in the three unknowns x1, x2, and x3. First, I think I'll do KCL at node A up here. The currents entering the node are equal to the sum of the currents leaving the node, so KCL at A says that U of t is going to be equal to the current in this direction, which is x1, plus the current in capacitor C2, which is C2 x3 dot, plus the current through this resistor, which is its voltage, which is just x3 over R2. Can solve this for x3 dot. So x3 dot is equal to U over C2 minus x1 over C2 minus x3 over C2 R2. There's my first state equation. If I call this node B, I can do KCL at B. That's just going to tell me that the current going into that node, which is just x1, is equal to the current through the capacitor, which is C1 x2 dot. Solving this for x2 dot is equal to x1 over C1. There's my second state equation. Finally, I'll do KVL around this loop. So I'll call that loop 1. KVL around loop 1 says that the voltage across the capacitor, x2, plus the voltage across the inductor, which is Lx1 dot, is equal to the voltage across the capacitor C2, which is just x3. So if I solve that for x1 dot, that's equal to x3 over L minus x2 over L. There is my third state equation. These equations are easiest to deal with if they're placed in matrix form. So let me write my matrices, x1 dot, x2 dot, x3 dot is some 3 by 3 matrix A times x1, x2, and x3 plus some column vector B times U. The first equation is this one down here. So x1 dot is equal to 1 over L times x3 minus 1 over L times x2. There's no x1 in this equation, so I can multiply that by a 0. There's no U, so I can multiply that by a 0. Second equation is just 1 over C1 times x1, 0 times x2, 0 times x3, and 0 times U. Finally, x3 dot is 1 over C2 times U minus 1 over C2 times x1, nothing times x2, and minus 1 over C2 R2 times x3. So here's my A matrix, here's my B vector. Now let's do our output equations for this circuit for a couple of different choices of outputs. The name of the game when doing our output equations is to write whatever output we choose in terms of the states. So here's our circuit with our choices of states. For one example, let's choose our output y of t to be the voltage across the capacitor C1. If this is the case, then y of t is just exactly the same as x2. So my output equations would be y is equal to some row vector c times the states plus some number times u. This is just x2, so this is 0 times x1 plus x2 plus 0 times x2 plus 0 times u. So this becomes a 0 times x1, 1 times x2, 0 times x3, and 0 times u. So in this case, this is my c vector, and my d is equal to 0. I can choose a different output if I want. So let's call the current through R2 my output. Say that's Y2 of t. In this particular case, Y2 is the voltage across the resistor divided by its resistance. If I do KVL around this loop here, this voltage is X3. So Y2 is X3 over R2. If I write that in matrix form, Y is equal to some row vector times the states X1, X2, X3 plus some number times U. Nothing times X1, nothing times X2, 1 over R2 times X3, and nothing times U. So in this particular choice of output, this is my C vector, and my D is still equal to 0. Next, let's do some simulations of the responses of these states. So for our MATLAB simulations, we need some values for the resistances, capacitances, and inductances. For our simulations, I'll choose R1 equals 10 ohms. R2 is equal to 50 ohms. I'll make L 1 Henry. I'll make C1 equals 0.1 farads. And C2 equal to 0.01 farads. So now we'll go to MATLAB. We also need a forcing function when we do our simulations. So I'm going to say U of t is equal to 3 plus 2 cosine of 2 pi t. And for initial conditions, I'm going to claim that those are all 0. So x1 of 0 is equal to x2 of 0 is equal to x3 of 0 is equal to 0. The circuit's initially relaxed. Now let's go to MATLAB and do our simulations. In MATLAB, I like to keep all my work in a script file. So I'm going to go to my previous folder, cd c:/tim/ssm_demos, which is where I saved my last demo. And I'm going to create a file called ex_2. First, I'm going to define all of my variables. So those are the resistance and capacitance values and the inductor value that I chose last time. Now I'll set up my A, B, C, and D matrices. So first row of A is 0 minus 1 over L, 1 over L. Second row is 1 over C1, 0, 0. Third row is negative 1 over C2, 0, negative 1 over R2, C2, and so on and so forth. There's B, C, and D is 0. I rather arbitrarily chose my output to be the voltage X3. That's not going to matter to me in this one because I'm going to plot the states themselves directly, so C and D will be more or less ignored when I get done with my plots. Our input in this problem doesn't fall into one of the categories of a step input or an initial condition or an impulse input. So this is going to use the LSIM command to simulate the response of the system to an arbitrary input. The LSIM command likes to have the system model set up as a structure, as a state space model. To do that, the command is SS, create a state space model. You send your A, B, C, D matrices to that, and you get a structure back that contains the properties of that model. Now, once I've got that, I can define my input. To define an input, you have to have the input as a function of time. So I need to define a time vector. I'm going to rather arbitrarily start at 0, choose time steps of 0.01, and end at 20. Now my input is just the function that I showed earlier, 3 plus 2 times cosine of 2 pi t. The syntax of the LSIM command is LSIM. You give it your system model, sys2, the input, u, and the time values at which u is defined. I can also provide initial conditions here, but since my conditions are 0, that will be assumed. I don't need to specify that the initial conditions are 0. Now if I do this command here, the response will be calculated and a figure will be created and the plot will be displayed. I'm going to choose to return the values for y, t, and the states x. So on the left-hand side of an assignment operator, the output, the time vector, and the states get assigned as a result of this command. So this is going to be a column vector. This will also be a column vector. This will be a matrix with 3 columns. The first column will contain the values of x1 as a function of time. The second column will contain the values of x2 as a function of time. The third column is x3 of t. After I've got those values, I'm going to go ahead and plot the response. To plot the response, the command is just plot. And the first line will be t, and then the second column of x. This colon notation means take all of the elements in that dimension, so all of the rows in the second column, then all of the rows in the third column. So this will plot the second state, x2, and this will plot the third state, x3, on the same plot. And this notation here tells me that the plot of x3 will be a red line that's dotted. Now let's save this. Run the file, ex_2, and there's my response. The blue line is x1, the red dotted line is x2, both as a function of time from 0 to 20. I probably should add some axis labels to this. So to label the x-axis, the command is xlabel, and then a string containing what you want to put on that axis. I'm going to say that's time in seconds. So now I've got a label on the x-axis. To label the y-axis, it's y-label. And these are both voltages, and their units are volts. If I chose, I could also put a grid on this plot. The command is simply grid. That looks messy, so I think I'm going to take it off again. Grid is just a toggle. If I do it again, if there's a grid there, it'll remove it. I think I'm done.